Okay, hello team. So we are back with a video where we're going to discuss gradient descent. Since I last talked to you when we were in class, we did a little reorganizing the schedule. We thought that there would be some times where we might need a few videos throughout the quarter to make up for the shorter schedule, but we reorganized things so that we should probably only need this one video as like that the extra lecture topic that we kind of need to get through that we don't have time because of the holidays and the structure for winter quarter this year. However, what that means is that this video is going to be slightly longer than I originally anticipated. This is going to be about a full lecture's length. Now, one thing to note is that this is a really important topic. It's one that you really should understand, but it's not something you need to rush through this second. It's not something that you need for homework one, but it is something that you will need for homework two. I recommend watching this video after Monday, January 29th's lecture on convexity, because we require a couple arguments from that convexity lecture in here. But you could also watch this now before then, and you'll understand most of it. But when I do start talking about convex functions, that some of those might not make sense until you watch the lecture that we all have in class on convexity. Okay, so we're gonna have one longer video for today about gradient descent and all the things you really need to know about it. There are a few things for today, namely one kind of larger example that is kind of outside the scope of what we're actually going to ask you to do, but I still want you to see it and be familiar with it at least a high level, because there are some interesting ideas that I'll try to make those parts very, very clear, where there's something I don't quite really need you to understand in full detail. Okay, so with that, let's dive into the discussion of gradient descent. So last time, we briefly introduced gradient descent as kind of this meta optimization algorithm. It's an algorithm that works in a lot of cases where you don't necessarily have a closed form solution to solve a minimization problem. So the idea for gradient descent was we have some cost function we're trying to optimize. In the case of linear regression, that was our least squares optimization metric, or error metric, which is the sum of the squared errors. And that forms a function that for any setting of our coefficients tells us how good or how bad that setting of coefficients is. And in the case of least squares, what this function ends up looking like, if you plot it for every pairing of two-dimensional inputs, W1 and W2, if you plot it, it forms something like a bowl. And so the idea with gradient descent was to start at some initial point and roll our way down the hill until we reach the optimum. And so we had to describe the mechanics for how do we actually roll down the hill. And the way we did that was using derivatives, or in higher dimensions, gradients. So the idea was we start at some arbitrary point, and then at every point, the slope, or the gradient, tells us which direction is downward. Well, technically, a derivative or gradient tells you the direction of greatest ascent and the rate of ascent. And so we always took a step in the negative direction, the negative gradient, or the negative slope. So in this case, if we started at W0, we compute the slope and find that the slope is negative at this point, which means that in order to get to the bottom of the bowl, we want to step to the right. So in that case, we want to increase our x when the slope is negative. And conversely, if we were on the right side of the bowl, where the slope is positive, we'd want to decrease our W0 so that we get close to the bowl. So what we found there was that this general update formula is start at some point W0, compute the slope at that point, and take a step in the opposite direction. So we subtract the derivative of that point. But we also multiply some step size eta, and that's a hyperparameter we have to choose that controls how far we step each time. Now, we're generally going to take small steps. So after one iteration, we have not yet reached the bottom. But what we could do is we could repeat this idea over and over. At every point, we compute which direction is up, and then step in the opposite direction so that we can go down to the bottom of the bowl. And we repeat this over and over and over again until we eventually converge. And usually convergence means that either your objective function value doesn't change too much, or the thing you're optimizing over, in this case our coefficients, don't move too much, for some definition of how far do you want to consider not enough before you consider yourself converged. Again, with numerical methods, we usually have to have a lot of these kind of specific constants for, okay, if you haven't moved X amount, then we'll consider it done in this case. Okay. That was all in one dimension, but in many dimensions, we call this a gradient descent, and the formula is exactly the same, except we compute the gradient at each point W, and then step in the opposite direction of the gradient, because the gradient is a vector that tells us the direction of greatest ascent, and again, we want to descent in this case. We also showed a kind of visualization of what this looks like, where we kind of start at some arbitrary W0, that has some loss, and that we showed how that corresponds to what model that corresponds to that setting of W, the first set of W's. And we saw that it's not a great model, which is corresponding to the fact that it's very high up on this bowl. What we do is each step we compute, okay, which direction of rate of change for this loss function, and then step in the opposite direction. So we'll update and go slightly down, which makes our function slightly better, but not good. It's not perfect yet, but we can keep repeating this over and over again, and this slowly improves our function until we get to the bottom of the bowl where we find our unique minimizer, in the case that this function is convex and doesn't have any of those kind of directions of indeterminate minimums where we said maybe if your data was correlated or you had too few data points for your dimensions. One kind of interesting thing to note about this kind of visualization of our loss function, where we have kind of our function, on the left-hand side, we have our function, the actual model that we're learning. On the right-hand side, we have this loss for every possible setting of those W's, is the shape of that bowl is actually determined by this matrix we use a lot, this X transpose X. So just as a reminder, this X transpose X is the sum of the outer products of all our data points xi transpose. And the eigenvalues of this matrix really tell us the curvature of this bowl that we're working with. So the important thing to note about that is that depending on how conditioned your data is, this bowl might be very steep or it might be very shallow, or in some directions might not have a unique minimum in the case where we had fewer data points than dimensions. So all of that is determined by the data that you're giving it. And the thing to note about that is that eta step size here, we generally have to change depending on the curvature of this bowl. If the bowl is really, really steep, in that case, we generally need smaller and smaller etas so we don't accidentally overshoot the minimum, that we don't take a step too far. A thing that maybe wasn't super explicit when we talked about this last time is I mentioned that eta controls your step size, but in reality, there's actually two things that control how far you step each time. Eta is a constant multiplier, but also the magnitude of the gradient. If the gradient is larger at a point, you're naturally making a bigger change because you're subtracting eta times the gradient. So if that gradient is larger, then you're making a larger step each time. Conversely, as you get closer to the bowl, hopefully the gradient is shrinking, and so you're naturally making smaller and smaller steps each time, even if eta stays the same. Okay? That's an important thing to note, is because sometimes if you have data that is maybe has this kind of really large eigenvalues, that means this bowl is really, really steep, you might sometimes miss the minimum. And that's something you have to kind of keep an eye on. I just wanted to mention that kind of relationship between the data that we're getting and that eta. So that eta kind of has to depend on your data. In general, though, you can, in some very contrived circumstances, solve for an optimal eta. But in general, for most real-world settings, we just try a bunch of etas and see which one works best, okay? Just try a bunch of them spaced out. Okay, so that was kind of the recap of what we did last time. And then we also had this kind of one last recap slide here about some of the things, some of the practicalities, like how do you choose W0? That's generally just start at some random point, or if you have a better guess, you can start there. That's totally fine. How do you choose eta? Generally, the step size matters because if it's too small, it takes a long time to converge. If it's too large, you might overshoot the optimal at the bottom, and then you might bounce away, which is not really that great. How do you choose? You can optimally solve in some special cases, but in general, another hyperparameter you have to choose. Generally, you try a bunch of different sizes of eta and see which one does best. We also generally said when to stop, which could be when you reach some convergence, you haven't moved too far, or in some certain cases, in particular with deep learning and neural networks, we sometimes are concerned with running gradient descent too long may actually lead to overfitting to our training data. And so oftentimes one form of regularization is to stop gradient descent after a certain number of iterations. And that, again, is yet another hyperparameter. We'll talk more about that later when we get to deep learning. Okay, so I want to do something that is different than what we did last time, is I want us to actually work through some examples of gradient descents with concrete functions that we knew, that we know. So for example, let's consider what gradient descent does with ridge regression. So we have the same setup for gradient descent, start at somewhere. In this case, I'm just going to start at 0. And then update each time the next set of coefficients as the previous set of coefficients minus eta times our gradient. So let's actually compute what this is if the objective we're trying to minimize is this least squares plus the ridge regularizer. Note in this formula, I'm multiplying everything by 1/2 just because it makes the math easier when we start multiplying by 2's, because when we're taking gradients, it doesn't matter because the thing that minimizes 1/2 f of x is the same thing that minimizes f of x, but it just makes my math slightly nicer here, so I don't have to worry about that. Okay, so if we want to write this out, we could do the same steps as we did before for when we were doing ridge regression, we're trying to find the closed form solution. Again, we'll talk about comparing if you could do both closed form and gradient descent later, but let's just pretend that we weren't able to do the closed form, and I want to see how I could do gradient descent here. I can rewrite this function. I'm just going to do it up here so I can have some room. Is going to be equal to y transpose y minus 2y transpose x w plus w transpose x w plus lambda w transpose w. Okay, so that's foiling out that kind of inner product that happens when we're taking an L2 norm. And then, so like the L2 norm of w is the same as w transpose w. Same thing for y minus xw. We could just FOIL out all of those terms. We did this in the ridge regression lecture. And just like in the ridge regression lecture, just also to simplify some things, we're going to combine that w transpose xw term with our lambda w transpose w to get y transpose y. Oops, my switch eraser. Y transpose y minus 2y transpose xw plus w transpose x plus lambda I w. So combining that into one term. Okay, so now that we have this function, we can take the gradient of it. The y's don't matter. That first term over here will simplify to oops, keep switching my eraser on accident. This will simplify to minus x transpose y minus x w plus lambda w. So we're taking the gradient of this with respect to w. All of this math works out here. Again, we skipped a step of taking the direct gradient and then simplifying terms. This is the same kind of equation we came up with here. Also, just to be clear, I should make sure that these are notated as WTs and not just plain W. So this is whatever our current set of coefficients is. So that's our gradient at that point. And in which case, then our update step will be WT plus 1 is equal to WT minus eta times this. So this will be WT minus, and note the first term is a negative, so that's going to end up being a plus eta times x transpose y. Oops, that's a weird looking y. Y minus xw at time t. And then this is going to be minus eta lambda wt. Yep. I could rearrange some terms here with the wt's and kind of factoring things out to simplify. And this will end up being 1 minus eta lambda wt plus eta x transpose y, whoops, again, weird looking y minus x wt. Okay, now the reason I simplified it in this way, or I moved terms around, is actually this kind of is indicative of what is happening in gradient descent with ridge regression. So this term here is the gradient direction just for our least squares objective. So ignoring the ridge regression part of it, this is actually the update step that would happen if you just did gradient descent on plain old linear regression. So it's kind of trying to change our W based on this kind of gradient direction of our least squares objective. So this term is kind of really just about minimizing least squares, or that it's changing W so that it's minimizing least squares. However, on the other side, this term is changing WT by some other factor 1 minus eta times lambda. And what this term is really trying to do is the shrinkage that ridge is trying to accomplish. So this is actually shrinking the coefficients of WT to be smaller based on stronger values of lambda. So if lambda is larger, that's going to make the values of WT even smaller. So this other part, this other direction that we're stepping in, so we're kind of taking a step in both of these directions combined. The first one's like kind of move us in the direction that minimizes least squares, while the other one is trying to move us in a direction that minimizes the norm of WT in such a way that it gets towards 0. And again, different choices of lambda will control how much we step in one direction for the other. So it's a nice way of kind of getting this intuition that running gradient descent you're really minimizing this whole function, but it does have this interpretation of kind of having this tug of war between these two separate objectives controlled by that lambda right there. Okay. So that's a formula you can use, and you can go into Python and you can write this up that you could start at some W and add on this gradient every single time, or subtract off the gradient in this case of descent, and it will update your W's over and over again until it actually minimizes, and you'll get the same solution as your closed form, assuming that everything is uniquely defined and that you let it run until convergence. So that's great. Let's do another example. Let's see, and this one's going to be more helpful for your homework too, which is, let's see what gradient descent, and this is what I wrote out on the slides earlier. Here, let's see what the gradient descent steps look like for lasso. So same setup as before, we're just doing gradient descent, but we're going to try to minimize the lasso objective, which is least squares plus the L1 norm. Again, scaling least squares by 1/2 just for simplicity, so that it doesn't affect, so I don't have a bunch of random extra 2's floating around when we're taking gradients here. Okay. So pretty easily, we can see from the last time that the first part of our gradient is going to be the same as the ridge regression case, the part that comes from least squares. So our gradient is definitely going to include this minus x transpose, y minus xw. So that part of the gradient is coming from our least squares objective up here. So that's going to be the same. However, there's going to be some more that we're going to have some another term in our gradient, and that's going to come from the L1 norm. So what we need to do is we need to actually compute what is the gradient of our L1 norm here. And just as a reminder, the L1 norm is equal to the sum from j equals 1 to d of the absolute value of wj. Okay? So we want to figure out what that gradient is. And just as a reminder, it's generally useful, especially if it's not obvious how to take a gradient right away. Whoops, I accidentally undid that. Don't want to do that. Is you can always compute it index by index. So let's compute what the ith index of this gradient is, and then we could put it together in this whole thing. So this would be the partial derivative with respect to wi of the sum from j equals 1 to d of the absolute value of wj. This ends up being, for all terms other than wi, 0, because all the other terms that sum are w1, w2, w3, all the ones that aren't wi. The derivative that with respect to wi is 0. So the only term that's left is the partial derivative of wi, or the absolute value of wi, sorry to make that more clear, with respect to wi. Now, if you don't remember what the absolute value function looks like, so for an input wi, this ends up looking like a v. The absolute value of wi is this v-looking function, where it's almost like the line y equals x, but on the negative side, it's the negative version of that. So one thing to note here is that the slope here, no matter what value wi is always constant, except for only depending on if it's positive or negative. So in the case that it's positive, the slope is positive 1. And in the case that's negative, the slope is negative 1. So one way to write this out is we can just say that this derivative, or the partial derivative with respect to wi, is just the same as the sine of wi. So when wi is positive, this partial derivative is positive plus 1. When it's negative, it's negative 1. Let's ignore for the fact that 0 is not, the derivative at 0 is not defined. We're just going to assume for simplicity that the 0 case is not there. But if we wanted to be more complete, we'd have to do some slightly other notation using this thing called a subgradient, which is not something we're going to talk about too much, but we will be mentioning in the convexity lecture that Matt will be doing next time. Okay? So that's going to end up being our gradient. And that means what we can do here is we can now, for our overall gradient, add on lambda times sine of w, where I'm applying the sine the sine function element wise. So it's saying, oh, is the element 0 positive or negative? Make that a 1 or a negative 1, and so on and so on. And that's how we're updating our gradient there. Okay, so that's our gradient. And now we just need to step in the opposite direction each time. So now we're going to take wt plus 1 is going to be equal to wt plus x transpose y minus xw. Oh, I forgot to multiply that by eta. Did I remember to multiply that by eta up here? I did. Yeah, okay, we're good. Multiply by eta, 1 minus xw. And then what I'll have is minus eta times lambda sine of w, t. I should make these indexed by t to make that more clear. Okay. So that's our update for our lasso objective, that we take a step in this direction. And what you're going to see in this homework is instead of writing it out like the sine function directly, we have a special piecewise function that says, okay, you step in this direction when it's this way, you step in this other direction when it's this other way, and so on and so on. Okay. Now, one thing to note about this, to note about how lasso works, is this term here doesn't shrink as WT small. Maybe let me move that over. Whoops. That's weird. Okay, we'll write that out again. Doesn't shrink with WT. Look, compare this to ridge. As our WT vector gets smaller and smaller, the step size we're taking, oh yeah, sorry, I knew I was missing an eta somewhere. I'm missing an eta right here. Okay, sorry about that. I'll make sure that's fixed here. Because eta is in this context fixed, it's still okay because we're taking smaller and smaller steps as we get closer and closer to that minimum, that the gradients that we're stepping with respect to is shrinking. So these step sizes are kind of naturally getting smaller. And in fact, as WT approaches 0, the adjustment due to regularization ends up also getting smaller and smaller because it's scaled by whatever value WT is. In the lasso objective, this is not the case. That we are taking smaller and smaller step sizes as the gradient decreases, but as we get closer to 0 due to that lasso objective, we're not actually taking smaller and smaller steps each time. We're taking the same step each time. So what that means in practice is, say, just for simplicity, let's just suppose you're minimizing the L1 norm, you're not minimizing least squares. If you start up here and you'll take some step size to the right, maybe I'll make that step slightly bigger. Then you'll end up here and take the same step size each time. Then when you end up here, you might overshoot, which then means you might go here, and then you might go back and forth, and you'll never actually hit that bottom because that step that you're making each time is the same because the slope never changes. The slope never decreases at any point, and your eta is staying the same. So you're always making the same step according just the L1 part. Again, ignoring least squares just for just 1 second. So what that means is with lasso, it is very possible if your eta, it's much more likely that if your eta is too large, that you'll actually just bounce around at the bottom and never actually reach the minimum. However, this is not too much of a big deal in practice because very commonly what many people will do is say, especially for lasso, use a decreasing size step size eta, so that as eta, or as you kind of reach this bottom, if you use a smaller and smaller eta each time, you'll be making a smaller and smaller step. There are other fancier algorithms that also try to figure out, hey, am I in this situation where I'm bouncing around, and then dynamically update eta? But also very commonly, people will just use something like start at an eta naught and then decrease it by some value of like eta over t or eta over log t or something, so that it's kind of decreasing over time. Okay. Again, which one should you use? Hyperparameter. You have to try it, see how it goes. Okay. So that is gradient descent for lasso. So now we actually have here kind of an explicit formula for how you make these steps. And again, you can code this up. You can say, okay, here's my current W. I want to subtract off these terms, and that will give you your new W. Keep running that over and over again, like you'll do on your next assignment. To make this a little bit more concrete, let's actually look at a code example that actually shows us what this looks like in code. Let me flip over to my Jupyter notebook. So this is a Jupyter notebook. This is posted on the course website that actually kind of just walks through an example of lasso that shows kind of how we're using gradient descent to minimize it. So we start off with defining the optimal theta. Here I'm using theta to describe the coefficients W. So I generate some random data X and Y, And for some reason, just for simplicity, I'm not actually including any noise. I'm multiplying the noise by 0. But if you want, you can change that and see how lasso responds to different various level of noises. Here I'm defining a cost function. So this is the loss that I'm trying to minimize. So the cost function takes x, y, theta, and our lambda for the coefficient for regularization. And it computes what is the least squared plus the lambda times the L1 norm. So this is actually some code to write up that formula for least squares plus the L1 norm. I also have my gradient step that takes my x and y, my current theta, or my current w. Alpha in this context is the step size. One thing to note, maybe is a little confusing, I should have used eta here, but one of the things we want to do is show you that actually lots of people have different common notations for gradient descent. Alpha is actually a really common variable for step size and gradient descent. Popular libraries like scikit-learn use the variable name alpha to describe the step size. So just wanted to get you familiar with different people use different notations. If this was a better example, I'd write documentation for what all of these meant. It'd be clear that alpha was the step size. And then also our lambda parameter for our regularization. And this also lets us control how many iterations we want to do of gradient descent. Okay? So what we do is just for the number of iterations we ask for, we take our current theta and we minus off alpha times all of this terms for the x transpose times y minus xw thing, or x theta in this case. And the derivative of the gradient of the L1 norm. And we'll just repeat that over and over again. This is the formula in code that we wrote on that last slide. Okay, so what I want us to do is I actually want us to show, okay, this is just some helper functions to do this, what happens in gradient descent. So I define my starting theta, I define my constants for my step size alpha, my number of iterations, and what my lambda penalty term is going to be. And then what I do is I just go through all these iterations and compute what is the cost function, as well as what's my error each time. And the reason that these are slightly different is the loss includes the regularization term, so that lambda times the L1 norm. So I want to show what those losses are, because that's the function I'm actually minimizing. But I also actually wanted to show what is my training error going to be at each step. So I just use my cost function, plugging in lambda as 0, because that's the same as the least squares objective. So I'm looking at both what's the total loss and what's the training error, because I'm going to end up plotting both of those later. And I just keep running gradient descent over and over and over, one step at a time, making it one step at a time and computing that. Now here I have some plotting code to actually show us what these results look like, just to walk through what it's doing, just so you get an idea of kind of what's happening here. We kind of define a set of an XY plane for all the possible values of theta 0 and theta 1. So we kind of define from some range of thetas, how many of them to evaluate at, and then this mesh grid kind of makes an n by n grid of showing us kind of all these possible points of theta. And then we go through and plot, okay, what's the cost function at each of those points? So how much does it cost? And then we make a contour plot that looks like this. So ignore this rainbow path for just a second. What this code up here is plotting is, whoops, sorry, that highlighted exactly what I didn't want to highlight. This first thing up here, what is plotting is our contour plot, these level sets of our objective function. So this is showing this top-down view of the bowl. So note that it looks like least squares, but it has these kind of weird sharp corners along the edges, along certain axes. That is precisely the effect of the L1 objective. Remember, the L1 objective is an upside-down pyramid. So the fact that our kind of bowl looks kind of like it has sharp corners is the result of adding on the L1 norm, which does have sharp corners. So this is kind of this combination of the two. If you ran this experiment again with larger lambda, it would look more and more like a pyramid and less like kind of a smooth bowl. Okay, so that's showing our cost function. So for every plug value of theta, what is the cost of the least squares plus lambda times the L1 norm? What this x is showing is the true theta. So remember, I defined the true theta at the top. And what we're doing here is with this setting of lambda, showing another way of looking the path that lasso is taking on each step of gradient descent. So we start at one point and we start rolling down the hill and we kind of reach towards this kind of minimum point down at the bottom. Okay? If you made lambda 0, it should, assuming you have enough data that kind of represents the space, this would equal to the least square solution. But in this case, because we know we're adding regularization, we're adding a little bit of bias towards 0. And so it's going to settle at something else. Okay. Now, one thing that's a little hard to see with this graphic as I described it is it looks like we kind of go down and smoothly converge at the bottom, but that turns out to actually not be the case. We actually run into the same thing as before, where if you look at the theta values, so what are the coefficients as this gradient descent progresses, you can see that the one of the thetas, sorry, one second. One of the thetas tends to increase and it starts to settle at one value. That's kind of the best choice of that theta. But the other one, as it's starting to get smaller and smaller, it reaches that point where the step size ended up being too big. And so we see this sawtooth pattern where it's happening is it's bouncing back and forth across the bottom of that bowl because it has that sharp L1 objective to it. And our step size is kind of not adjusting for that. So what you could do is you can run this with a smaller eta, or you could say run it instead of using a constant eta, like I mentioned, using a decreasing eta over time. And that could help you avoid this sawtooth. But when you see this sawtooth pattern, especially with lasso, that often means you're in this case where you're kind of near the bottom, but you keep jumping back and forth over it. Okay. And here you can see the cost function per iteration that is decreasing. But again, at that bottom, we kind of run at the sawtooth. So this first graph, or the second graph, I guess, not counting the 2D plot, this one is plotting the coefficient values at each point, and this is plotting the overall cost function. You can see, again, we kind of sawtooth at the bottom. Whenever you see sawtoothing with gradient descent, it means, even without lasso, it means you're generally in this case where you're kind of bouncing back and forth across the minimum. So that usually will mean that you need a smaller step size if you don't want to do that. Okay, so that is gradient descent. So awesome in practice, or awesome in theory too. But what I actually want us to do is, I'm going to switch back to my slides, is I want us to talk about a variation of this gradient descent algorithm that's actually going to be much more commonly used in practice. Well, we'll talk about it in a particular format that's not quite used in practice because it's more intuitive, and then I'll tell you exactly how the people do it in practice, which is basically the same idea. So here we just say our gradient descent demo. And so I want to talk about this modification of this algorithm called stochastic gradient descent. And this is kind of the powerhouse algorithm that is more commonly used in theory. There's a slight modification that actually is used in practice that I'll talk about at the end. Okay, so gradient descent, awesome. Let's just optimize any function. And a guarantee that we have is if the function we're optimizing is convex, it's guaranteed to find the global optimum. So in this case of least squares, assuming you have well-conditioned data, you have enough data points for your dimensions, so you don't have any of those half pipes that are kind of that kind of let you have an indefinite number of solutions along some dimensions. If that's all true, you're guaranteed with gradient descent, if you let it run long enough, it will find that optimal solution, which is great. However, and I should mention, in the case that it's not convex, you have no guarantees about the quality of the solution, but that doesn't stop people from using them. So even in the case of like deep learning or neural networks, those functions, the cost functions that we're optimizing for tend to be extremely non-convex, but gradient methods are still some of the most popular ones to use, despite having no formal guarantee of giving you anything good enough. And we'll talk more about that when we get to deep learning. But just want to mention that these gradient-based methods are what we use even in non-convex settings. We just lose a lot of the guarantees that we get for the convexity. Okay, so gradient descent is really cool. It's a very powerful algorithm, but as I described it to you, is not exactly what's used in practice. So I want to add just a little bit more notation, and then I want to describe a really big problem with gradient descent as we describe it. So just to make this discussion a little bit more general, to move away from least squares or ridge or lasso, and I want to talk about gradient descent more generally for minimizing any cost function, I'm going to introduce the notation here of the general loss function. So a loss function is going to tell you for any setting of coefficients how bad, what's the cost of that setting of coefficients, and then generally we're trying to minimize that. So in our case, this loss Li of W is equal to the squared error on the ith training point. Okay. Now, in general, you can make this any function that measures error, but what we've been doing so far in almost all these examples is minimizing squared error. So Li is the error or the cost on the ith training point. And then maybe to make this more general, what I can define is, L of W is equal to the average loss on all our training points. Okay, so L is the overall loss on the whole training set. Li is the loss on the ith training point. Okay, again, you could just think about this as squared error, but these L functions are supposed to be more general, that they can represent any kind of error metric that you might want to come up with. Okay, so gradient descent then, in that context, is taking our current W, subtracting off the gradient of the loss function at that point, and in this setting, it's the average loss over all our LIs. Now, maybe this wasn't clear before when I was showing you those gradient descent examples, but maybe is a little bit more clear in the way that I wrote this here, is computing this gradient actually it seems to be kind of complicated. That for every step of gradient descent, I might be taking thousands, it's not tens of thousands or millions of iterations to converge to my optimal. At each and every step, in order to compute that gradient, I have to loop over my whole training set to compute the loss and then compute the gradient of that loss. So that's a lot of looping over your data set. And you can imagine pretty quickly that if you have a large data set, like a gajillion points, that this is going to take a long time for every single step you have to make. So gradient descent, great in theory, but tends not to work as well as practice on most real-world data sets because it just takes way too long to compute that gradient every single time. So instead, what we're going to do is we're going to use an estimation technique to speed this up. And the estimation technique we're going to use is what we call stochastic gradient descent. So instead of computing the full gradient over the full loss function, what we're going to do is we're going to run almost the same gradient descent algorithm, but instead of computing that full gradient over the full training set, we're going to estimate our gradient using a very particular mechanism. So instead, we're going to take the gradient with respect to W of something else that in theory, or we'll show, is going to estimate the full gradient. So what do? We're going to take out of our n data sets, or data points in our data set, we're going to draw uniformly at random one of the indices. So I'm going to just select data point 23. And then I'm just going to compute the loss function on that data point. So I'm just going to say, okay, what was the y value for index 23? What was the x value? Multiply that by my current W, square the error, and then take the derivative of that, which would be 2 times that in the 1D example. So I'm just going to say, okay, that's my gradient, and use that as my update step. Okay. So instead of computing the gradient of the loss function over the whole data set, I'm hoping that just by computing the gradient at one data point, that's hopefully good enough, or that's a good enough estimate. Now, why does this work in theory? Well, it works because this estimate gradient actually is an unbiased estimate. So if I look at what's the expected value of the gradient, this is equal to the sum from I equals 1 to n of the probability that my random index at time t is equal to index I times the gradient of the loss of the ith data point of W. Now, this, simplifies because the probability of selecting any individual point is just 1 over n. This simplifies to 1 over n times the sum from I equals 1 to n of the gradient of Li of W, which is just equal to the overall gradient of L of W, which is this formula right up here. So because I'm sampling uniformly at random, in expectation, the estimate of my gradient by just using 1 point is actually the overall gradient, which is great. So that means I'm getting an unbiased estimate of my gradient. And now you can imagine how this speeds things up greatly. That now, instead of having to run over my whole data set, I just pick 1 point and step in the direction that point tells me to minimize. Now, however, though, we don't get something from nothing. That by doing this to speed this up, there is actually going to be a cost. And that cost is for stochastic gradient descent. My optimization tends to wander a bit more because while this gradient estimate is unbiased, it is a very noisy estimate because I'm trying to estimate a loss of maybe a gajillion points with just 1 point. You can imagine there's a lot of noise there. And so generally when you're using stochastic gradient descent, you have to make your eta, your step size, much, much smaller so that at each time you're not actually jumping as far because you're not using a very accurate estimate, even if it's unbiased, in expectation, right? So we generally see that stochastic gradient descent tends to wander around a bit more unless you're much tighter on your eta step size to make sure that it's not going too far. Okay. However, we'll see at the very end that there's one more modification we can make that's actually used in practice. to not make that kind of noisy estimate as much of a big deal. But right now, plain old stochastic gradient descent, sample one data point, use the loss function for that single data point to estimate our gradient, and then step in the direction or the opposite direction of that, what that says. Okay, so that's kind of what we're saying. This is just a written down version of this slide. Okay, so I mentioned earlier at the very beginning of the video that there's a lot of important things to understand about gradient descent. Everything I've covered up so far is really important to understand because they're things that you use in practice. What I want to do for the next about 20 minutes or so is I want to show you a more theoretical example that I'm going to show off a theorem that is, or a common type of theorem that's shown for stochastic gradient descent. I want you to understand at a high level what the theorem is saying, and then we're going to prove the theorem, but I don't want you to worry too much about the proof. And the reason for that, we're still showing it, is because it actually is this type of proof comes up a lot, especially when you're working with these kind of optimization algorithms. And it has a lot of neat tricks that you might find useful. But I want to clearly say, though, that the exact details of the proof aren't the most important thing that matter. I'm not going to ask you to do a proof like this one. So it is okay if the details of the proof don't make complete sense. But I do want you to see it and kind of appreciate some of the steps, because there are some really cool techniques that you could use in your own proofs, if you're ever trying to prove something, that you might find useful. Okay, so again, I'll try to highlight those important bits and pieces, but it's okay if the whole proof does not make complete sense. But I do want you to understand, at least at a high level, what the theorem is saying, but again, the proof not as important. Okay, so there's lots of things you can prove about stochastic gradient descent, but one of the most common things that you start off with that are very useful is how we think about how it converges. So we're really interested in asking, well, okay, is estimating in this way even guaranteed to have any guarantees of convergence? Are we going to actually find the minimum, or are we just going to wander out in space? And maybe we want to ask, how quickly does it converge? Or at what rate does it converge? Okay, so that's actually what we're interested in here in this theorem, is asking, okay, how bad is our estimate from stochastic gradient descent compared to the optimal? So I'm going to go through all these parts here because it has a lot of assumptions to it, or a lot of setup. And then, so I want you to understand this slide, and then the rest of the proof I'll kind of walk through, and then we'll talk about it in detail. Okay, so what is this theorem saying? So we're starting with our standard stochastic gradient descent setup. So we're going to let W of t plus 1 equals WT minus eta times our estimate gradient by sampling a point or index IT uniformly at random. And what we're interested, and again, so we already said that, the expected value of this estimate gradient is equal to, in expectation, to the overall gradient. And then we're going to make a couple assumptions. Don't worry about them too much. We're really just trying to put some restrictions on kind of the format of our problem. So this first one, actually, there's a typo here. This is supposed to say W star, where W star, oh, this is actually kind of a big pen. Hold on. Let me make this a bit smaller. I think it's this one. So W star is the true minimizer. W of our overall loss. So this is the sum over all data points of the average loss on each point. Okay. So this is saying here, let me try to write this out nicer with my smaller pen, that, there we go. So this first condition is saying that our W0, where we start, how far that is from our W star is at most distance R. So we're saying we're within R units of distance from the optimal. So, if you start further away, kind of naturally you can imagine that you're going to either take longer to converge, or you aren't going to have as strong as guarantees. So we're saying you start at most R away from the optimal position. And then this second condition in red here is saying that the gradients don't get too large. That at most the magnitude of any gradient is at most G. If you are in 546 or you did the B problems, this is the same as on homework 1, where we had a condition that was L Lipschitz. In this case, this is a similar condition here, that the gradients aren't getting too large. Now, the notation here is a little complicated. We're doing a maximum over all indices I, so we have to look at the gradient at each data point, and we're looking at the magnitude of that gradient. But the gradient is also with respect to the W, so whichever W we're using, which changes throughout the gradient descent step. So we have to actually look over, at least in theory, all possible W's. We want to make sure the gradient of the loss isn't getting too big. And this soup notation is a lot like max, but instead of being the maximum value, it is the lowest upper bound. And that sounds maybe kind of verbose for no reason, but it has to do with the fact that maybe that this number G isn't actually in the magnitude of any of the gradients, because it's an infinite set, that it's just the lowest value that upper bounds any magnitude of the gradients. Again, sounds a little verbose, but is kind of needed in practice, especially when we're dealing with these things. So the supremum of a set is the lowest value that upper bounds at all the values in the set. Okay, so it's kind of, again, still an upper bound on everything. Okay, so we upper bound our gradient magnitudes by size G for any W. In practice, and you can actually get this slightly better, but you actually don't need to do the supremum over all W's, just likely W's that you're going to hit around your optimal. But the notation for that's a little bit more complicated, so we're just saying we're using a looser requirement that over all W's, the magnitude or the gradient of the coefficient doesn't get too large. Okay, so if those things are true, we're doing stochastic gradient descent. We didn't start too far away. We started at most R away. And then for all of our W's, our data is conditioned well, or data and loss functions are conditioned well enough that the gradients aren't too large, or at most G. If that's the case, then I can make this claim. And that's what this last sentence is saying. It's saying that the expected value of the loss of our average iterate. So what is this? W bar. W bar is the average set of coefficients across my whole gradient descent path. So it's defined over here. This is saying that over each time t, I'm just averaging what all my coefficients are. Now, when you use gradient descent in practice, you almost always are just taking the last step as your optimal. But at least what we're going to do in this theorem is we're just proving that, along the path on average, we're looking at that average loss, or the loss of the average point. Okay, and that's just because the math for the average works out easier. But you can also try to do a theorem like this for the endpoint as well. Okay, so I'm saying the loss of the average set of coefficients we visit along our path minus the loss of the optimal coefficients. So I'm essentially asking, how bad is the loss incurred by gradient descent relative to the loss of the optimal predictor? Okay, so we're just asking, okay, how much better are we doing? Or how, in this case, how much worse are we doing than if we knew the optimal solution from the get-go? And what we're going to prove is that you can upper bound this loss. That you could say, actually, especially even in squared error or any other loss case of loss for any step size, what I can say is I can upper bound how bad it is by this equation R, which is again how far off we started, over 2t eta, where capital T is the number of iterations we did, and eta is our step size, plus eta times G, the size of the largest gradient, over 2. Okay. So that's a function that we're going to show that we can get that. That's telling you, okay, how bad is your loss going to be? Well, it's going to be at most this bad. In this setting, just think of R and G as constants that you can try to compute, or you can try to say, oh, I know based on my setting that these are the maximum values of them. This now gives you a formula for a given eta of how bad your error is going to be. It's going to be at most this. So you can get some strong guarantees about that the error will be less than this. Now, if you set eta particularly, that if you set to minimize this upper bound, so to get the best upper bound, the smallest upper bound for this, you could choose eta carefully. And the way to do this is you can take the derivative of this with respect to eta, set to 0, minimize. And if you choose eta to be the square root of R, the distance from the optimal, for the starting distance from the optimal, over gt, g again the maximum gradient, and t is the running time of this algorithm, then you can find that this formula is upper bounded by square root of rg over t. Again, think of rg as a constant. So what this means is that our loss is, well, again, big pen. I want to go back to my smaller pen. My loss here is going to be big O square root 1 over t. Now, this is cool because what this is saying is as you increase the amount of iterations, the difference in your loss, that you're getting better and better, that difference goes down in a rate of 1 over square root t. Now, this is super interesting as a theorem because it has no dependence on a lot of important factors that matter for a lot of other algorithms. So for example, there's no dependence on the number of data points n. And this is incredible of a result Because what this is saying is if you let the algorithm run long enough, that you can get really, really close to the error of the optimal W star, the true minimizer of the coefficients of the training error for the whole data set without needing the full data set. You only need to look at something related to T steps. So you have to choose T carefully, and we'll talk about that in just a second. Oh, actually, I'll talk about that now. Sorry, I was just looking at my notes. So that means if n is a gajillion, there's a lot of data points. But you just want your error, you want your error to be something like epsilon. So you want to say, like, I want to be within 1% of the optimal. Well, in that case, you only need T to be about 10,000. You only need to take 10,000 steps of gradient descent. And according to this theorem, ignoring, again, about 10,000, because I'm ignoring some constants, about 10,000 steps to find the optimal, or within the optimal W within 1%. That's just 1% is 0.01. 1 over square root 0.01 is, or solving for T when that is equal to 0.01 is about 10,000. Again, solving for R times G is 1. Not, people don't come up with exact numbers because, again, these RG numbers are generally hard to compute in practice, but it gives you a sense of scale. That this is telling you that you need approximately, T is approximately epsilon to the negative 2 steps. So for every setting error that you're comfortable with, that's approximately how many steps you need to take here. This is exactly why in these super large language models that are kind of all the rage now, like ChatGPT and that stuff, the way they train is they actually run over their whole data set only once. Because even though they're optimizing for a really complicated function that maybe you might theoretically need in most settings, might need to run gradient descent for a really long time, what they end up doing is they kind of just run it, looking at each data point only once, and they can actually still get a pretty good set of parameters, one that can make ChatGPT, despite the complexity of the problem. This maybe goes along with the next point that this bound doesn't depend on the dimensionality D of our parameter set. Maybe that's a better argument for why they only loop over their data set once. Okay. So if your data set is in a random order, you can't just sort it by some value because then you might get some weird dependence going on there. Then you can make some really strong guarantees here. This is great. This is a really powerful thing about stochastic gradient descent. It's why it's an algorithm that's used, or at least in theory, in lots and lots of different settings, because it has a lot of these great guarantees. This is just one possible theorem that you can come up with, but there are many other theorems that you can make as well. Okay, so that's our theorem, that this converges at a particular rate, and that you can set that rate depending on constants that you know, or you can upper bound those constants if you're unsure. But this is telling you that you're getting closer and closer to the minimum under some loose set of assumptions. Now, what I want to do for the next 10 or 15 minutes is I actually want to prove this result to you. And again, like I mentioned, the details of this proof aren't the most important, but I do want you to understand at least some of the tricks, because these tricks are useful, and I'll highlight what those tricks are. So we're going to try to prove this claim. Okay. Now, I'm going to be trying something new here where I'm going to animate in parts of the equation so you don't have to read my nasty handwriting by erasing some. I covered everything in white. This may or may not work. We'll find out. It's an experiment in practice. The proof is also a little unintuitive in some ways, because I'm going to start nowhere where we'll expect to. And at the end, we're going to end up where we want to with our theorem. So I'm kind of organizing this a way that I think makes maybe not the most logical sense from like your start point to end point, but I'm going to try to make it so that it's the least jumps as possible, so that we're not just saying, okay, I'm starting here and doing these random transformations. Maybe this, where I'm going to start, seems a little bit weird, but I promise you we'll kind of go back to where we want. So I'm going to start by proving something about a different value that is not in our theorem. So I'm going to start with how far away we are at time t+1 from the optimal. So remember, our theorem is about the difference in the losses of the average place, the loss of the average place versus the loss of the optimal place. Instead of talking about losses for a second, I'm just going to talk about actual distances. So how far away are we in the L2 norm at time t+1 from the optimal? Okay, that's where I'm going to start by proving. I want to show that we're kind of we're going to be not too far away, kind of depending on kind of how far we're stepping each time. Okay, so how far are we at time t+1 from the optimal? Well, at time t+1, I'm just going to plug in here the equation for how gradient descent operates. So how do you figure out what time t plus 1 is? Well, you start at where you are at times t, and you subtract off the gradient times eta. Okay, that's just the formula for gradient descent. Now, what I'm interested in doing is in my next step, see if this works. Uh-oh, where's my eraser? I'm going to pause this for a second. Okay, figured it out. Sorry about that. Okay, so I'm starting with, I'm trying to figure out the distance between time t plus 1 from our optimal. And I'm to figure that out, I just plugged in what's the definition for gradient descent of how we make these updates. Okay, next. What I'm going to do, that didn't fully erase. Okay, now what I'm going to do here is I'm going to do some foiling. So what I'm going to take is kind of like we were doing that step earlier. When you're trying to figure out this norm, it's the same thing as kind of taking apart the vector transpose times itself. And then especially when those are sums or differences of different vectors, you can have this like a times a transpose a minus b transpose b minus 2ab or something like that. I'm going to take that for this kind of whole equation, wt minus eta gradient lit of wt minus w star. Okay, I'm going to FOIL all of that out, and then I'm going to separate terms. And so what are the terms that we end up with? So the first term is how far, and I'm going to group them. Sorry, I should make this more clear. I'm going to group them such that I have wt minus w star as kind of one term, and then it's minus eta times the gradient as the separate. So I have two terms here that I'm going to FOIL out. Okay, so that first term is just going to be the norm between wt and w star, so how far we are away at time t, minus, this is kind of the cross term, 2 times eta of the expected value of the gradient at time t at point it times, or inner product with the distance between w transpose and wt and w star. And then plus our squared term for the gradient step, which is eta squared times the expected value of the gradient. Again, that's just foiling all that out. Okay, so now that we're there, there's some important things to say about this. So if we start at some distance, and our hope is to get closer to the optimal at time t plus 1, then what we need to make sure is that this term over here is overall decreasing our distance. So what we need to make sure is that for our particular setting of eta, that this term ends up being larger in magnitude because we're subtracting than this term that we're adding. So this works generally well for small values of eta because eta squared is a smaller value if eta is less than 1. So generally eta is going to have to be a smaller value. Again, you can figure out what that optimal eta is, but I'm just trying to point out that what we're doing is we're setting eta is we're making sure that it's small enough such that this term is decreasing at each step rather than increasing. Okay, that's what we're usually guessing and checking. Okay, so that was foiling things out. A little complicated, not clear why we were doing that. But now what I want us to do is I want us to kind of do kind of a magical step here. Is I'm going to upper bound this distance. So I'm going to say, okay, my distance at time t plus 1 from the optimal is equal to this thing I FOILed out. And now what I'm going to do is, because it's really hard to compute those things exactly, what I'm going to do is I'm going to say it's at most these. Okay, so at most this. So the first one, I'm going to go to so the first term is the same. The first term is the same. Not going to change that at all. The last term is going to be at most n squared g from our assumption earlier that the gradients are at most g. So that means for any w and for any I, the gradient is at most g. So now I'm upper bounding this distance by saying it's at most eta squared g. So I'm just plugging in this value is at most g into my equation. Okay. Now note, I also changed the middle term that I kind of separate mini proof for that. So I'm saying is that's at most the expected value of the loss at time t minus the loss at times of w, the optimal. And that's not clear why those are the same from this equation. So what I want us to do is I want us to do a kind of, I want us to do a little mini proof here. Eraser. A little mini proof here to talk about this term. The expected value of the gradient of the estimated gradient with index I, t, with the inner product of wt minus w star. So I'm interested in figuring out what do we know about this thing. So the problem here, let me hide that. The problem with this term is it's really hard to compute as is. And the reason for that is both wt is a random variable and it is a random variable. And the reason for that is it is clearly a random variable because it's a random index that we chose at this point to estimate our gradient. But note that wt is also a random variable because where we are depends on the random set of choices we made in previous iterations. So it's really hard for me to analyze this, especially because it's a product, that I have a product of a times b where both a and b are dependent variables. And so it's really hard for me to say a lot here. So we're going to do a trick, and this is a trick that we've seen a few times, especially in Homework 0, where it helps to add conditioning in expectation. This is sometimes called the law of total expectation or law of iterated expectation, where I can now condition on something but add an extra expectation, and that will give me the same result. So what I'm going to do is I'm going to condition on the entire past of our algorithm. So I'm going to add a condition on what the random point we made at I1 and I2 and I3, and so on and so on and so on. And now at this point, I've added outer expectation because that's necessary for this. At this point, the only random variable I have here is it. Because wt is no longer a random variable. It's deterministically determined by the sequence of random choices we made from time 1 to time t minus 1. If you know all of those choices, there's no randomness involved. So I'm conditioning on all of those. So now the only randomness here is at time t, which index I'm picking. This is great because now this expectation is easier to solve. Because now the expected value, this inner expected value of the gradient transpose the difference between wt and w star, the wt minus w star is no longer an expectation, right? No longer a random variable, so that's just a value. So I can pull that out of the inner expectation. So that means we're just left with the expected value of gradient lit wt. And like we said before, the expected value of our gradient for index it is just the overall gradient. So now I can kind of simplify those two terms. So now it's just the expected value of the entire dataset gradient at term wt, inner product wt minus w star. So again, let me just repeat that just for clarity. I first use the law of iterated expectation, law of total expectation, to add an outer expectation, and in my inner expectation, condition on the past. Now that we conditioned on the past, I can now move that wt minus w star out because that's no longer a random variable conditioned on the past. And using our proof from earlier that the expected value of our estimate gradient is the whole gradient, I now essentially get rid of that inner expectation. I just have the outer expectation of this. Now, what I can do is I can lower bound this term. The reason I'm lower bounding is because I'm trying to upper bound this equation up here, and I'm subtracting this term I'm working with right now. So I'm trying to upper bound something, but I'm subtracting something. I want to find a lower bound for the term I'm subtracting so that it upper bounds my overall term. Kind of weird because the negative there. Now, why is this last statement true? This last statement is true just due to the statement of convexity that Matt is going to talk about on Wednesday. So just as a reminder, if you have seen this lecture or if you haven't, I'm not going to prove this statement, but we'll talk about it on the convexity lecture. If we know L is a convex function, which we do, because I'm just going to assume that it's a convex function, then I know that for any convex function, convexity says that f of y, for some point y, is greater than or equal to f of x plus the gradient of f at x transpose times y minus x. So you can see here that my last term got erased or reerased. This last term, or the second to last term up here, is kind of this form, gradient times a distance. And that looks something like this. And so I could rearrange terms here to say f of y minus f of x is at most this kind of linear approximation of the function using that gradient as an approximator. So this is at most the difference of the losses between WT and W star. Okay. Quick recap. Started with the distance, foiled things out. I upper bounded the gradient term up here because I knew that our function is G Lipschitz. And then here, I'm lower bounding this term, so I can get an upper bound on the whole equation, by doing this conditioning step and then applying definition of convexity to give me a lower bound for what that is. And that is saying that's going to be at least the difference in the losses at time t and the loss of the optimal. Okay, so with all of that together, now I have a formula, an overall formula for what is my expected loss at time t between and time w. How do I do that? I'm just taking these terms over here and our left-hand side of the equation and rearranging terms. So I'm moving over this expected loss in the middle. And what I'm doing is then moving everything else to the right. So I'm saying the expected value of the difference between our loss at time t and our loss of the optimal is at most 1 over 2 eta times the distance between where we are at time t from the optimal minus the distance between where we are at time t plus 1 and the optimal plus eta squared times g. So this is giving me an upper bound on my loss, or my relative loss from the optimal. Okay, I know, not the most clear proof, but what we're doing here is we now have only a couple more steps to put this together and make our steps. But what were the important things from this slide? So the first is upper bounding and lower bounding. Almost always in many real world settings that we care about, it's really hard to come up with exact terms for what we're dealing with. So using things we know about, say, convexity or independence or kind of assumptions about how big or small gradients are, we can usually upper bound or lower bound these things appropriately so that we can actually get something that we can work with. Okay, so we're almost there, almost at the form that we want. The biggest problem, though, is that this statement is just about the loss at time t, and our theorem was the loss of the average iterate over all steps of gradient descent. So that's kind of what we need to work on next. So in order to get there, what I'm going to do is I'm going to take the loss at each time t and sum them up. So to get to our gradient descent algorithm, I'm going to look at the sum of the losses starting at t is equal to 1 up to t is equal to capital T of what is our difference in the loss and the optimal loss at each point. So what I can do is I can just plug in what we just computed in that last line. I said, okay, well, I know it's at most this value. This is just plug and chug with this at most 1 over 2 eta. We're almost getting there. What I can do now is I can, whoops, too much. I'm going to simplify this. So this is a sum of this kind of complicated term. And between this line and the next, you see that the sum kind of disappeared. I want to talk about why, because this is actually a really useful trick. So the first term, or sorry, maybe I should start with, just for simplicity, this last term just becomes t eta squared g because that doesn't depend on the summation over t at all. So it's just t times that. Okay, so I'm just moving that aside. So really, I'm just trying to worry about what do I do with this thing, okay? Now, this is a really useful trick, especially when you're working with summations, because the format of this summation is a sum of differences. And those differences change based off index. So we're taking expected value of the distance at WT minus W star minus the expected value of the difference between WT plus 1 and W star. The thing to note is on different iterations of this for loop, these terms are repeated, and sometimes they're added and sometimes they're subtracted. So let me just do a simplified example real quick of this. Suppose I had the sum from I equals 1 to t of xi. Maybe I'll do t. Maybe we'll make these indices t just for simplicity or consistency. T equals 1 to capital T of xi, xt minus xt plus 1. So on the first iteration, I is 1. So we have x1 minus x2. On the next iteration, t is 2. So we add on x2 minus x3. But note, on the previous term, we subtracted x2. And on the next term, we add x2. So they cancel out. So this ends up being just x1 minus xt plus 1. That's capital case. This is what we call a telescoping sum. And this works great for a lot of proofs where you have this kind of sum of differences. And the difference of our particular form, where kind of so you subtract off what you add in on the next iteration. So that's what we get here in our kind of final result. is that almost that entire summation cancels itself out, except the first term and the subtraction of the last term in that whole sequence. Okay? So this is an exact equality for the telescope. So we still have an inequality from earlier. We proved an inequality above, so this is an inequality. But between the first and second line, that's an exact equality. There's no upper bounding of it there. Now, finally, we're almost there. There's just two more big steps I have to do. The first is now I have this form in this way. I can now upper bound this distance here by at most r. And the reason I know that is because our assumption r is that the distance between the starting point and the ending point, or the optimal, is at most r. And subtracting off anything is only decreasing that. So here I'm just saying, okay, at most this is r. So now we have at most that this whole sum is r over 2 eta plus t eta g over 2. We're almost there. But note, the thing we're calculating on the left-hand side of this inequality is not the same as what we're calculating, what we want in our theorem. In our theorem, we wanted the expected value of the loss of the average iterate. And here I'm just summing up the losses at each time t. So it's not quite there, we're almost there. So the last super powerful trick that I'm going to use in this proof, so the trick that's useful to know, whoops, let me go to eraser, is what we call Jensen's inequality. So Jensen's inequality is like a super powerhouse identity for when you're working with convex functions, and especially with random variables to do with convex functions or sums to do with convex functions. So for Jensen's inequality says for any random variable z and some convex function phi of the expected value of z is going to be at most the expected value of phi of z. Now what that means is that we can do often, because we know that our function is convex, we can kind of move around between summing a function and taking the function of a sum. We'd be using Jensen's inequality. So I'm going to do that by saying, hey, so remember that thing that we actually were interested in computing? The theorem said the expected value of the loss of the average iterate minus the loss of W star. Well, that's just equal by definition of what W bar is the loss of the average iterate minus the loss of W star. And now I have this kind of sum going on here. I have the expected value of a convex function, the loss of a sum. And what I can do is now, using Jensen's inequality, upper bound that by moving the sum outside and the function inside. So now what I could say here is that the expected value of the loss of the average is at most the average of the expected values of the losses. So I'm just using Jensen's inequality here. It's not using the exact form as written up here. If you check out the Wikipedia page for it, they show you actually a much more useful identity that has to do with a convex function of a finite sum. But that's the form I'm using here. But it's more generally written as Jensen's inequality in this way. And now I have here that this is at most 1 over t that sum. And now plugging in my value of my sum for that sum term I came up over here, just over 1 over t, now we have our proof. Now we said that this is at most r over 2t eta plus eta g over 2. And that's exactly what we had over here. Okay, that was so much work for a proof that I didn't fully want you to understand, so it's okay if that didn't fully make sense. Again, let me quickly recap the most important points that I do think are useful to know because they are useful tricks. So again, the first one was upper bounding functions that we don't know how to actually compute. So knowing when to upper bound something or lower bound something is a very useful technique. Other things that we used were the law of total expectation, or the law of iterated expectation, that we use to help us solve for random variables that we didn't know, especially that they were dependent on each other, by adding conditioning. And the other was the definition of convexity, again, that we talked about on Monday, to figure out, okay, how can I talk about these gradients times this kind of difference, this kind of estimated value function, or estimating a function using its linear approximator. Okay. And then the other important things were the telescoping sum, again, a very useful thing if you get lucky and your formula is of that form, and Jensen's inequality. So again, these are some tools in your tool belt that combine in a really pretty way to get this kind of elegant theorem. But it is okay if all those details did not make sense. That is a little more complex than we're going to ask you to do. Okay, so that's the end of the proof mode. I want to talk about a couple practicalities before we wrap up. Now that we kind of saw an example theorem and how it's really pretty and how there's a lot of math that goes behind it, I want to talk about some practicalities of using stochastic gradient descent, and thinking about why we use it in this way, and one other fix for a problem that I introduced earlier that I did not say. So the first thing I want to talk about is when to use this stochastic gradient descent method. So in particular, you might be wondering, hey, for ridge regression and for least squares, ordinary least squares, we have a closed form solution, but I actually did a lot of this work assuming we were using least squares or ridge regression. So if I am able to solve in a closed form, would I ever use stochastic gradient descent or would I not? So the first thing I want to do is I want to try to compare how does stochastic gradient descent compare with if you know the closed form solution. Okay, so let's start with comparing with the closed form solution. Whoops, that's laser pointer mode. Compare with closed form solution. And let's just do least squares for simplicity. Yeah, I just want to talk about least squares, but this applies to ridge as well. So as a reminder, for our closed form solution, we had our data matrix X that had Xi transpose as the first row, and then Xin transpose as the last row. Then we had our Y matrix that had Y1 all the way to Yn. Okay, and as a reminder, to solve this, we said, okay, W hat is equal to X transpose X inverse times X transpose Y. Okay, so how complicated, how much time does it take to actually compute this thing? So to compute X transpose X, this requires N times D squared flops. A flop is a floating point operation, so addition, subtraction, multiplication, division. So not often one way of counting steps is just how many kind of basic arithmetics do you need. This ends up needing N times D squared operations just to do this kind of X transpose X. So you have the sum from I equals 1 to N of Xi transpose. So this is making a D by D matrix. You have to fill in D squared values, and you're doing that N times and summing those up. So it's going to take a decent amount of time to compute this. Also, in terms of memory, you have to represent this D by D matrix this whole time. Okay? But this is actually not even the most complicated part of that. The most complicated part is to compute X transpose X inverse. And this ends up being D cubed flops. Turns out that in most practices, computing a matrix inverse tends to be one of the hardest things that you will do in practice on your computer, especially for large matrices where D is quite large. D cubed can take a long time. You might not even, in many cases, be able to represent a D by D matrix on your computer. So trying to invert something that takes D cubed time can actually take a decent amount, a long time. What that means is overall, to do the closed form solution, you need something like ND squared plus D cubed operations here, which could be done, which may take a long time. Now note, just like in homework 1, we told you that in practice, don't actually take the matrix inverse, solve the system of linear equations, X transpose X times W is equal to X transpose Y. But most approximate solvers out there, especially like np.solve, if it's ever using an approximation, those approximations tend to be different variations of algorithms like gradient descent. So it's kind of cheating by using gradient descent so that it's faster, because doing this exactly is often hard in practice. It takes just too long. Okay, so it would be kind of unfair to say, oh, well, linear.solve actually does this faster than this, because yes, it actually does it using gradient descent or something like gradient descent. So how long does it take gradient descent to work? Or in this case, let's just look at stochastic gradient descent. So per iteration, we're only doing about D flops of computation. We sample one point, and we have to compute its gradient, which requires looping over D components of our vector, and then it's adding on a D-dimensional vector and a D-dimensional vector, or subtracting, I guess. So it's about D flops per turn. And how many turns do we want? Well, iterations is just T operations. So that means overall, you're doing T times D flops to run gradient descent. And as a reminder, earlier I said you can set this equal to some epsilon so that your T has to be on the order of e to the negative 2. So this would be equal to D e negative 2. So if you want to be within some epsilon distance, then it's going to be approximate to d times epsilon squared. So that's the kind of runtime. So in many real world settings, gradient descent is much, much faster. We didn't do any analysis for plain gradient descent, but you can come up with a similar bound. It converges differently, but you can come up with a bound of the same type, but the formula is going to be different. So in many, many real world settings, solving things exactly, even if you have a closed form solution, just won't work. Okay? So we often use gradient descent because it's not too bad, or stochastic gradient descent. So that's one practicality, is that you often use this even when you have closed form solutions available to you. The one other practicality I want to leave us with is I mentioned earlier that stochastic gradient descent, even though it has some great properties, great theorems that go along with it, it's also actually not used as described in practice very often. And the reason comes from that downside I said earlier, that even though the estimate of the gradient is unbiased, it tends to be noisy. So a very simple fix to that is, instead of using one sample to estimate your gradient, choose some hyperparameter b and take b samples from your data set and estimate the gradient that way. And the great thing about that is now you reduce the variance of your estimate and gradient, which means you should hopefully be getting closer and closer to the true gradient each time, so that you're taking a better informed step at each time rather than a completely random step. And now that should hopefully help you converge faster. So in practice, people do this thing called mini batch stochastic gradient descent, which is exactly SGD as I described, except of choosing 1 point to estimate the gradient, you choose b points for some hyperparameter b. Now, the nice thing is that this reduces the variance in our algorithm. Note, this is not the same as reducing the variance of our model. That's about bias and variance in terms of like thinking about model complexity. All I'm saying is that in our algorithm, we're estimating gradients, and I'm reducing the variance of those gradient estimates. So I'm hopefully getting something closer to the true value, or the true gradient each time. So this reduces the gradient. Oh, sorry, this should not say 1 over square root b. This should say about 1 over b. So it reduces the variance of each step. The other nice thing is most GPUs are able to do these gradient computations in parallel. So if you give it multiple data points, it can compute those gradients in parallels. In fact, most of the biggest achievements in GPU design improvements over over year has to do with having larger and larger memory spaces to do these gradient computations. So you can use larger and larger batch sizes in the same amount, or in a fixed set of memory. So better GPUs have larger sets of memory that you can do these computations in. Okay. So that's basically it. You're just taking this kind of estimate, and this is generally the algorithms used in practice. How do you choose b? It's a hyperparameter that you have to kind of adjust for. Generally the larger and larger value of b should theoretically be better, but then it generally takes more time. In the worst case, where b equals n, that's just plain old gradient descent. So you want something smaller. And what we find in practice is that you can generally increase b up to a point. And then kind of after that point, you see kind of minimal improvements in kind of the steps that the model is taking each time. And it's not really worth the extra computation, okay? How do you figure that out? You try some, or you just use the largest size available for your computer. Okay, so that's all I really want us to talk about for gradient descent. Very, very powerful set of algorithms and variations of them that are used in practice, like mini batch SGD. And you'll find that we can use that all over the place for our models. So that's all we have for gradient descent. Again, that proof stuff is stuff that we can kind of skip over, but I want you to at least see it because I think it's a very useful idea. But the big ideas of practicalities for gradient descent are very important things, and ones that you will be using in the future. Thanks so much for watching this, and I'll see you all next time.